Okay, thank you very much for coming and joining us for this AI and data talk series, guys. So thank you for your continuing support for this actually series that looks at the interface, looking at the interface between AI and control systems or control theory in general. So today, the talk of today is given by Dr. Lam or Keung Lam, and has a title as Explainable Control Systems from Interpretable Fuzzy Models to Explainable Control Framework. So Dr. Lam is a reader in the Department of Engineering at King's College of London. His research focuses on control theory and intelligent systems, particularly fuzzy modeling, fuzzy model-based control, neural networks-based control, and stability and robustness analysis. He is an IEEE Fellow for contributions to the analysis and design of fuzzy model-based control systems and has been recognized as a Clarivate highly cited researcher since 2018. He is the author or co-author of several books, including Stability Analysis of Fuzzy Model-Based Control Systems, Polynomial Fuzzy Model-Based Control Systems, and Interval Type 2 Fuzzy Model-Based Systems. He has served and continued to serve in editorial roles for a number of international journals, including as a section editor for the Journal of Engineering, senior editor for IEEE Access, and more specifically the System Men and Cybernetics section, and an associate editor for few journals. We cite from them actually the IEEE Transactions on Fuzzy Systems, IEEE Transactions on Circuits and Systems, to Express Briefs, Neurocomputing, etc. So we have the list of the publications of Dr. Lam. He's available in his personal Google Scholar actually link or website. You can actually get more information about the publication of Dr. Lam. So Dr. Lam, actually before actually handing over actually to you to start the presentation, just for the audience, if you have a question, leave the question at the end. You can actually write them in the chat, and we can pick them up actually at the end. So Dr. Lam actually can look at them and answer them. And if you want to ask actually a direct questions at the end, then you can do so. Just you raise your hand, and then actually you will be given the chance to directly address the question to Dr. Lam. Dr. Lam, the floor is yours, please. Welcome actually Dr. Lam actually to give this presentation, guys. Thank you.
Yep. So thank you very much. Yeah, and also introducing me and inviting me to give this presentation. Yep. So as you can see that today the presentation title that is Explainable Control System, and then a few keywords that is about in this work we are talking about how to use the fuzzy logic system and then to integrate that or to realize the explainable control framework. So my name is Keung name, or you can just call me HK, and then that would be easier to remember and pronounce. Yeah. Okay. So okay. Just a little bit about my research background. I think that Labil already mentioned about my research expertise, and then which cover fuzzy model-based control. I will touch a little bit about this today, as well as different kind of machine learning and neural network-based control, and all of them together. We have extended that to the fuzzy explanation modeling so that we come up with the explainable control framework. So this is the pipeline we are going to integrate all the existing work from my team and then to put it into the explainable control framework. And also in the middle, that is something about the contribution and editorial role. I'm not going to repeat this. Okay. For today's talk, I think that it will be all about the explainable control framework, and I will focus at the very high level, but try to talk about try to explain how, what, why, where. When I talk about how it means that I'm talking about the methodology and the framework, what the XCF, the explainable control framework, look like, and then how do we realize that, and what it is going to do, and how do we use the fuzzy logic and then use it to translate a black box into a transparent model, and then integrate that into, for example, a large language model in order to provide human understandable explanation. Yeah. And then finally, I will also talk a little bit about the future vision, as well as what kind of thing we can achieve using the explainable control framework. Okay, so now for this page, it may look very complicated. I try to simplify that. This is basically, we can consider that this is the table of the content of today's presentation. First, I will talk about the motivation and challenges, why we need to have explanation for the control, or for the control strategy, policy, or a closed loop system. And then in order to provide explanation for a control system, what kind of technology we can use. In this talk, I will mainly focus on the fuzzy logic system, or the fuzzy logic technology, in order to realize the control, in order to realize explainable control. And then later on, I will talk a little bit about how do we make use of the existing fuzzy control theory and then integrate that into the fuzzy control, explainable control framework, in order to provide the initial design, and then translate into human understandable form. So that is 4, 5, and 6. It means that in order to translate the control system into a control theory that could be understood by human, we need to identify some of the gaps, why we have these challenges, and then how do we overcome these challenges. Using, for example, we have proposed the fuzzy model agnostic explanation, that is to translate some complicated mathematical model into a transparent model, and then it will become one of the components of the explainable control framework. Yeah. In the bottom, that is about the general idea how to realize the explainable control framework, XCF. That is, we have a control system, and then we are going to, for example, using some data-driven approach, and then we make use of the FMAE, fuzzy explainable modeling, or fuzzy model agnostic explanation structure, in order to provide the explanation. And then later on, we try to have different kind of explanation indicators and semantic information. This kind of thing, which is going to translate the complex model into something human can understand. And more importantly, it is going to work with the large language model in order to provide different kind of decision-making logic, as well as the explanation report to different user groups. Okay, so let's take a look at the motivation, why we need to do the explanation for the control system, and some big picture about this. Yeah. So the first thing, that is, when we talk about the control system, what actually it is. Let's take a look at this system. This is a closed loop system, a closed loop control system, which consists of three main components. The first one, for example, we have a linear system, whatever things right here. But on this slide, I use the drone as an example. That is, we would like to control the drone flying from point A to point B, and then the point B information that is given right here as the input. Yeah. So at any time instance, we can have some sensors or measurement which is going to measure, for example, the XYZ coordinates of the system or the drones, and then this information will be used right here to generate some information. The information could be the error distance between the current position and the target position of a drone. And then we have in the middle a controller which is going to make use of the error information to generate the control signal in order to realize this control objective. Altogether, we call this is a closed loop control system. Yep. Okay. So when we look at this control system, for example, I just extract this part. I just extract this part right here and then put it into this diagram. It means that if we would like to generate the control signal, we need to have some input in between. This is a controller. So we can imagine that this is a robot which is going to control the drone. Yeah. So how do we design this controller? Basically, there would be two extreme methods. The first one, what I mean the extreme method, that is, it could be a hybrid of these two methods. The first one, this is the analytical or the model-based design. So that is, we can use some classical control method, optimization-based control theory in order to design this controller. The advantage of using this method, that is, we have a rigorous mathematical approach to tell us how to design the system. But the thing is that when the system becomes more and more complicated, it is quite difficult for us to design mathematically this controller, yeah? Especially when the scale of the system becomes larger and larger. And also if we consider more complicated scenario, say disturbances, as well as some uncertainty or even some unknown parameters in the system. And then this approach may not be a very good method for us to design a well-performed controller. Yeah. And also another thing that is, when we have the mathematical transparency. For example, we have some theory tell us how to design. So that means for control engineers, they know everything, but it doesn't mean that it is transparent, because if it is difficult for us to explain this theory to different user group, for example, a lay person or maybe a project supervisor, whoever. Yeah. Okay. So another one, that is, this is the data-driven approach or the learning-based design. It means that we do not need to know anything or a limited stuff of the model or the nonlinear system, that is the drone. And then we use the data-driven approach. By learning, it is possible to make use of the input and then generate the output right here to control the drones. The good thing is, we do, as I mentioned, it is not necessary to know much about the model, and then everything by tuning, it is possible to come up with a well-performed controller. Yeah. But the thing is that if we are going to use, say, a neural network, which is going to serve as the controller, and then when we look into the neural network, it is just a bunch of the numerical values. We are not able to make sense of it, and we are not able to explain why we come up with that numerical value. And when we input something into the neural network, we just know that we have a control action, but we do not know why in this scenario or at that instance we have that numerical value. So these two are the general approach available in the control literature to design a controller. Yeah, of course, it is possible to combine both of them to come up with a hybrid control theory. That is, some of them, it is designed by analytical approach, and then so the remaining part of the controller, it is possible by learning. Yeah. Okay. So, but anyway, both of them, it is difficult to explain to different user groups. Yeah. Okay. So take a look at this one. That is, why do we need to have the explainable ability? Yeah. So this is the reason, because for the moment, no matter what kind of control theory, data-driven, learning-based, or the analytical approach, when we talk about some safe, safe critical applications, something like the autonomous vehicle system, robotic system, and then all this kind of thing. That means we do not only just try to make it work. We need to know why it works like that, why we produce control action, so that one, it is possible to open the black box to know how do they make the decision, and then it is, for example, for the safety concern, and also it will come up with some important information for us to use it as the feedback signal in order to improve the performance as well. Yeah. Okay. Now take a look at this one. That is, when we talk about the interpretability, it means that the model itself, it is able to provide some understandable structure. Yeah. So this understandable structure, that is for human. Yeah. So that means when we take a look at this example, when we talk about these linguistic rules, if speed is high, distance is small, and the braking force is large, and then so I think that this sentence basically can be understood by human. Yeah. But now, why I mention about this, it is because that in many of the models, they only provide some mathematical explanation. It is not quite possible to translate that into these rules using linguistic terms to explain what is going to happen. So now that means the first point is, if we are able to translate those mathematical model, mathematical controller, or even neural network black box model into these rules, and then so that would be a very good step for us to open the black box of a complicated controller. Yeah. But the thing is that even though we are able to translate a complicated black box model into an interpretable model, it doesn't mean that it is explainable. The explainability, it means that we are going to have mechanism to help people to understand the behavior and the decision of the model. Yeah, so that means the limitation right here, that is, even though we have these kind of linguistic rules, if the number of rules, say 10,000, and then so although when we look at each one of these rules, it makes sense to us. But when we are going to put them together, it is still not possible to have a good understanding. All these rules work together. Yeah. So this is about the interpretability as well as the limitation. That means the interpretability. It doesn't mean that it is explainable. Yeah. Okay. Now we are going to look at some fuzzy logic foundation. Yeah. What actually it is. When we talk about the fuzzy logic, it is a kind of technology which is going to mimic the human spirit. Let's take a look at this example. This example is that we are going to drive a car and keep a safe distance. Assuming that I'm driving the blue car, and then I would like to keep the distance, keep a safe distance. In my mind, I will come up with these rules. Of course, different people will have different rules, but they should look more or less the same, or the logic should be more or less the same. So take a look at this one. Rule number one, if this distance is small and then the speed is low. Yeah. Okay. Now maybe we are going to look at the next slide, which is going to have an animation. You would know better what I mean. Now I'm driving this car. if the distance, sorry, if the distance is small, I'm going to keep the speed is low. If the distance is medium, I'm going to keep the speed to be medium. If the distance that is large, and then I'm going to increase the speeds in order to reduce the distance. So everyone will have something similar, and then that means when we use this fuzzy logic, it is possible to translate complicated control action into something that could be understood by human. Yeah, so this is the fuzzy logic. And then take a look at this one. So that means now the control action or the control objective, that is to keep safe distance. And then how do we realize that? That is, we are going to use our eyes to estimate the distance. And then this distance will be processed by our brain, and then our brain will make a decision so that to control our arms, our legs to operate the vehicle. Yeah. So how do we do this? Basically, this is the basic structure of a fuzzy logic system. And then now assume that this distance, that is 3.5 meters. Now I use my eyes to estimate that the current distance, that is 3.5 meter. This 3.5 meter, it is not necessary to be accurate because when we talk about the fuzzy logic system, it is possible to deal with some uncertain information at the input. But in this talk, I'm going to skip this, but assume that now we have 3.5 meter. Now, I'm going to use the versifier, this versifier, which is going to translate this distance into something human is familiar with, that is small, medium, and large distance. And then the translation is something like that. Let's take a look at the x-axis, that is the distance right here, that is 3.5 meter. And then we are going to evaluate how small this distance it is, how medium, how large, when we are going to draw a vertical line. And then we just find out that how small it is 0.25. And then how medium it is 0.83. And then how large it is 0. Yeah. Now we call this is the membership function right here. So we have three trapezoidal membership function to quantify how small, medium, and large. How do we design these membership functions? According to our knowledge. Yeah. Okay. Now, when we are going to translate the number into small, medium, and large, we will work with the roots I just mentioned about. We have three roots, for example, and then based on these three roots, and then with this membership value in the y-axis, and then we come up with this information. Look at the root number one, because it is just right here. We have small. It means that 3.5, that is 0.25 of small. It means that the root number one will only contribute, for example, 25%. Note that the sum of these values, they are not one, or altogether, not 100%. It is because I haven't yet normalized that. Okay, but anyway, we can use this information to tell how much contribution root number one will be made. Similarly, the root number two, 0.83, it means that majority of the contribution will come from rule number two. And then for rule number three, 0, it means that definitely it is not high speed, because when the distance is large, the contribution is 0. It means that the speed is right here. If this rule is matched, and then the speed is high, but now it is 0, so definitely not high. Yeah, so that means altogether we come up with some information at this output. That means we are going to aggregate all these rules. Note that in the fuzzy logic system, all the rules, they are going to work together. They will interact with each other. Yeah, so that is, we will not just use one single rule to do, to contribute to the control action. Altogether, we come up with. That means in this situation, the input is 3.5, and then the speed should not be very low, and then more toward medium, and then definitely not high. So for this statement, basically, it is understood by human, but if it is not understood by the machine, so we need to translate this statement into a numerical value so that the vehicle will know actually what speed it is going to use. For example, 20 miles per hour. Yeah. So right here, because I mentioned right here that 3.5 meter, it may not be the exact value. So instead of using one single membership function, it is possible to use the type 2 or interval type 2 membership function in order to adjust the uncertainty. Yeah. But for today, I'm going to skip about the type 2 and the interval type 2, but just give a very brief introduction about that. It is possible to adjust the uncertainty of the input. Okay. Now, so that is, when we are going to use the fuzzy logic system, we are going to use the linguistic rules to explain what is going to happen. When we look at this structure, all of this structure with the rules, with the linguistic variable, it is possible to translate some complicated control action into linguistic information people can understand. Yeah, so that is the reason why we are going to use the fuzzy logic as one of the tools in order to implement the explainable control framework. Okay, so when we use the fuzzy logic system, there are some unique features. First, the rule structure. It is interpretable. Yeah, translate the complicated control action into rules. So because of this, it made the model transparent. And then by looking at every single rule, it is possible to decompose the behavior, because rule 1, that is considering the distance is small, rule 2, that is to consider the distance is in the medium. We just break down the complicated control action into small region and small local explanation. Yeah. So altogether, it gives us some sense about how to understand or how to review the decision-making process of a model. Yeah. Okay. Yeah. Now, at the moment, I talk about the fuzzy logic, why we use the fuzzy logic as a tool to describe the model to make it transparent. I talk about using the analytical approach as well as the learning-based control to realize the control system. In the remaining part, we're going to talk about, although we have these rules, and then how do we generate these rules, as well as how do we create some indicator so that people, as well as the large language model, can understand better about what is going to happen at different instance or in different domain. Yeah. Okay. Now, just going back to this diagram, that is, we already cover point number 1 and point number 2. Now I'm going to talk about the existing work of the fuzzy model based control, which will give us some idea how to use the mathematical approach to design the controller. Okay, now this is the explainable control framework, we would like to use the explainable control framework to explain how AI controller work. So this AI controller, including the analytical controller, as well as the data-driven controller. Now, that is, you can see that we have four main components. The first one, that is the closed control system, and then the next one, that is we already have the fuzzy logic, and then which is going to create the fuzzy explainable model. Yeah. So fuzzy logic, that is a tool how to create this model. We are going to use the FMAE, the fuzzy model agnostic explanation approach, to create these rules. And then later on, we need to have some explainable indicator to review or to open the black box to tell a little bit more details about what decision the model is going to make, and then generate the human understandable explanation using the large language model. So take a look at this one. The idea, that is, I just try to summarize what I have covered for the closed loop system, and then go a little bit more details about the remaining part. Yeah. So we are going to have a drone to control, use the sensors to measure the distance, and then I'm going to create a black box controller that would be something like a robot, and then this robot is going to monitor the situation of the drones and then generate the control actions right here, and then so which come up with a feedback loop. Yeah. And then so, but when the drone crashes, and then we would like to know why it crashes. That is, the explainable control framework is going to play the role. How to do it? We are going to before moving on, and then I would like to highlight one thing, that although I mentioned about the closed loop system, yeah, but if we do not consider the feedback loop, and then the overall framework still works. For example, when we talk about medical image slides, this is we would like to have an AI control detection model to tell us whether it is a cancer or non-cancer image, and then we can still use the fuzzy logic to tell us about to provide us the explanation. Yeah. But anyway, so it means that I'm talking about for closed loop system or the open loop system, the framework still worked to provide the explanation. And now, how do we provide the explanation about the behavior of this robot? What we are going to do, that is to collect some data, and then to create and then create an explainable model. This interpret model, we use the fuzzy logic to create that, and then later on we come up with another translation layer to provide the indicator. And what it means is that we can consider that this is the original model, and then that is right here, the black box model. And here we just come up with an algorithm to turn the controller, the black box controller, into a surrogate controller, a simplified controller, for example, working in a certain domain, so and so. So this is about the fuzzy logic model, or the fuzzy model. And then the next bit right here, that is the explainable layer. What it means is that after we turned the black box model into a simplified model described by if-then rules, we are going to do some X-way. We are going to look into this model so that we will have some more information what the model actually is working on. For example, when we look at the rules, and then we know about the activation, we know how much contribution each rule is going to contribute to the final decision making. I will give an example later on. Yeah. Okay. And then the next part, that is, we are going to put all of them together into a structured semantic representation. What it means, that is, we can imagine that we collect all these if-then rules, we collect all this semantic information as well as the indicators, and then put it into a template, and then this template that could be understood by the large language model in order to generate the visualization as well as the explainable report. Yeah, so that is what I mean about for the last part of this diagram. Okay, so sorry, right here, when we talk about the fuzzy model based control, and then this is a kind of analytical approach. So that means when we are talking about this closed loop system, we come up with a drone, we have the sensors to measure the coordinate. We are going to design this controller and generate the control action. How do we design this kind of things? Yeah, as I mentioned earlier, we can have the learning based approach. We can have analytical approach, but right here, I'm going to introduce the fuzzy model based control. And then the fuzzy model based control, that is, we are going to use a fuzzy model to describe the drones using if-then rules. By looking at the then part, it means that we are going to break down the complicated model of the drones into something simpler. For example, we are going to use a linear model. That means right here, in this region, we are going to use the linear model 1 to describe it. In the another region, we use the linear model 2 to describe it. Yeah, so that means why we are going to do this, it is because that the linear model, it is easier for us to understand. I mean, the control engineer to understand, as well as easier for us to design the controller in this region. But altogether, it is still the original complicated model. And also the most important thing, that is, we are able to use the fuzzy logic, the linguistic statement to describe the behavior of this model. So when we look at this format, we have if and then this is the linguistic structure. Similarly, when we have this model, we come up, we are going to design this robot, and then we are going to use similar format. If then, that means corresponding to this region, we come up with a linear model, linear controller to control it. So we have the linguistic rules to describe the behavior. Yeah. So the advantage of using the fuzzy model based control approach is that we have some rigorous analytical approach to tell us how to design the control gains, that is the parameters of the robot. Now, when we look at the model, we are not able to design the parameters of the control of the model. It is because it is given by the drones, but according to the analytical approach, which will tell us that how to choose the value of the K, how to choose the parameters of the robot, so that the system is stable, subject to our control objective. Yeah. So that means using the fuzzy logic approach, it is possible to have some beautiful theory to tell us how to design the parameters. But the bad thing is that when we use this approach, it is still not quite possible to provide explanation because everything is described by mathematics. But when we compare that with the traditional or the classical control, we have the linguistic rules to give us some idea how to interpret the operation or the model decision behavior of the model, but it is not the best one. So that means when we use the fuzzy control approach, that will be one step closer to the explanation. That means that is the reason why we need to have the next approach, the fuzzy model, the FMAE as well as the XCF, in order to provide the indicators, semantic information to generate the linguistic explanation or the natural language explanation to different user groups. Okay, so for this slide, probably I'm going to quickly go through that. So when we use the fuzzy model-based control, and then these are the timeline about the research and our research group, one of the main contribution, that is to propose this kind of membership function dependent approach. It means that it is possible to, when we do the stability analysis, it is possible to come up with a less conservative stability analysis result. So what it means by that, it is we can just simply put it like this. For traditional fuzzy control approach, in some cases, it is not possible to come up with the design which is able to stabilize the system. But using our approach, and then we can design these control parameters to stabilize the system. So this is about the advantage of the fuzzy the MFD analysis. Yeah. Okay. So some example about using the fuzzy logic control or the fuzzy model-based control. This is the some simple experiment about the bolt tightening control. Yeah, so this is about the using the fuzzy logic controller to control the continuum manipulator, and then so we also apply the fuzzy logic control as well as the decision making to do some robot sockets and some simple experiment about inverted pendulum, and work with the graph neural network to do some navigation of the mobile robot. Yeah. Okay. Now we already cover about why we are going to use the fuzzy model-based control, because it is possible to come up with to have some analytical design as well as the model or the controller is semi-transparent. Yeah, and then now in the remaining part, I'm going to talk about how do we make use, or how do we translate this complicated control behavior into something we can understand. Yeah. Okay. Let's take a look at this one. So up to now, as I mentioned, if we are going to use the analytical approach, what we come up with, that is some mathematical approach to tell us how to control the system. It is still not yet can provide some explanation, for example, to explain the behavior, to tell us how to understand the decision is going to be made by the model, so and so. Yeah. And when we talk about a purely data-driven control approach, and then everything, it is just a numerical value. We do not know. We only know that the model is going to generate the output, but we do not know why it generates the output like this. Yeah. Okay. So this is the gap about the current situation. So now what we would like to do is, even though we have the initial design that is a black box, and then we are going to use the fuzzy model agnostic explanation, which is going to generate an interpretable fuzzy model. And then this fuzzy model, which is able to provide us some explainable indicator and semantic information, for example, the rule base, so that all together right here, it is able to work with the large language model to provide some explanation. And then this explanation that could be translated to for different stakeholders. Yeah, something like the engineers, decision makers, so and so. Yeah. Okay. Now we are talking about, I mentioned many times about the FMAE Now I'm going to talk about what actually it is. That means if we refer to the block diagram right here, I'm going to talk about these two components right here, which is going to translate the robot into a transparent model. And then this transparent model, it is possible to come up with some rules, if then rules that people can understand. I don't mean that we are going to translate that into, for example, 1,000, 10,000 rules. And then so we have some algorithm that is to translate this complicated model into a few rules within a small domain so that people can understand. Yeah. So let's take a look at the idea about this. So the XCF, this framework will consist of these four main components. The first one that is the control system, and then this control system, we are going to see something like that. This is the control to closed loop system I mentioned before. We use the data-driven approach or the fuzzy model-based control method to design this controller. And then this controller, that is either a black box or it is difficult to explain. And then so we try to create a surrogate model. So we are going to sample the controller, come up with the data set, and then feed it into the explainer. This explainer, that is the FMAE, how do we generate the fuzzy model for this controller that is able to be understood by human, yeah, using the fuzzy rules and some indicator. Okay. So once we have this data set, we are going to translate into the rules. When we talk about the fuzzy model agnostic explainable model, it is not just simple, just one layer, and then or just a bunch of these rules. And then so we are able to provide multi-level explanation. What I mean a multi-level explanation, that is, it is possible for us to explain one sample instance using these rules. If we are going to consider, for example, this region right here, and then we call this as a local explanation, that means it is possible to aggregate these rules for one single point and then have some abstraction and then to describe the area right here using different set of rules. These rules will be less complicated and then people can get a high level understanding about what is going to happen and then how the model is going to behave in this local region. If we are going to combine this local region and then we have the algorithm to come up with the aggregation mechanism to group all these rules into another level of explanation. We call this is the domain explanation, and then all together we come up with another the global explanation right here. Yeah, so it means that is the idea. That is something like right here. We can imagine that if we are going to look at the global explanation, that is the universe, and then when we zoom into different area, we can see the planet. When we zoom in to the planet, we can see, for example, mountain, clouds, air balloon, or something like that. And then so when we zoom into this mountain, it is possible that to see there is a tree. So this is what I mean, the multi-level or the hierarchical layer framework for the FMAE. So we have different algorithms to upscale by aggregation or downscale by simplification to provide this different kind of different layer of explanation. Each layer of the explanation that will be facilitated by different set of rules, and then so we have the simplification algorithm so that although the original model that will have maybe 1,000 rules, but it is possible to reduce it into a few number of rules. Yeah. Okay. So So now this is about the FMAE. So I still have a few slides to cover, and yeah. Okay, so a quick comparison between the XCF and the existing explanation method. For example, when we talk about the sharp line attention visualization, all of them, one, they are designed for classification, static approach. Yeah, so that means when we talk about the control system, we will have the dynamic behavior and then the temporal information. So it is important for the XCF to capture these kind of information. Yeah. So okay. Now when we talk about the indicator, that is, for example, when we talk about these rules, and then when we say that this rule that is coming from the example of keeping a safe distance in the vehicle control. Yeah, distance is small, the speed is high. Now I'm going to consider more information in order to control the braking force. So when we look at this one, we will have the rules to provide the explanation. Second, we corresponding to each rule, it is possible to tell how much contribution each rule is going to provide. When we zoom into each small portion right here, distance is small, it is possible to provide us how each parameters or how each input distance and speed is going to be evaluated by small or high. How small is the distance? How high is the distance? So that it is going to break down all this information into these small pieces so that which can reveal more details about the explanation of the overall control decision. And then also graphically, it is possible to draw something like this. Yeah. So x-axis is the distance, and then y-axis, that is the speed. And then we come up with some graphical representation. Here, the red region, that is the emergency braking region, so and so. Yeah. So this is something the XCF can provide, that is, the traditional approach cannot. Yeah. Okay. So quickly, very simple example. Yeah. Now we have an autonomous vehicle braking scenario. This scenario, that is, we would like to keep a safe distance. Currently, we measure the speed is high, the obstacle distance, that is, these two cars distance, that is close, and the road friction is low. And then we come up with these rules. So for each rule, it is possible to come up with the contribution number 0.91 for the rule number one. Speed is high, distance is close, and road friction is low, and then the braking force is very strong, and so and so. So that means for 2, 3, 4, and then we come up with these values. These values already tell us that which rule provide the contribution. And then now if we are going to ignore 0.31, 0.17, it means that the first two rules, which is going to play the major role about the control action by looking at these rules, which will give us some ideas how the model is going to behave. Yeah. Okay. So this is just to demonstrate how the explanation is going to generate, as well as we can describe the control explanation using the rules as well as some indicators right here, for example. Yeah. Okay. Quickly, the future vision, and then now that is we for the XCF we have these components: framework, explanation mechanism, as well as how to generate the rules, as well as how to generate the indicator, how to work with the large language model. All together, today I just present some high-level ideas, but how actually each component is going to work, how to generate the algorithm and mechanism, and then there are still some open question. Yeah. Okay, so I know the time is very tight, and then so quickly I'm going to talk just a few more slides, and then it is possible to extend this idea into different kind of application. For example, autonomous vehicle, reinforcement learning, and then this kind of application. Now, the conclusion. Today, the XCF, our vision, that is just to we are not going to only to design a control system that is high performing, but we also like to have a framework which is going to open the black box, the controller, to make it trustworthy. Yeah, so this is the vision. And then the last page, that is about the achievement and the resources. If you would like to have more information about the fuzzy model-based control, these two papers. If you would like to have more information about the fuzzy model agnostic explanation framework and some XCF framework, and then these three papers for the open source resources related to these papers, please refer to these GitHub resources. Yeah. So thank you very much. Yeah. So this is my presentation for today. Yeah.
Thank you, Dr. Lam. Much appreciated, actually, your presentation. I'm not too sure if we are nearly exceeding time, actually, by 1 minute. Is there any quick question for Dr. Lam? If not, actually, we will actually move forward, actually, to thank Dr. Lam for his presentation. Please, if you have any question, you could raise your hand and you can directly address it to Dr. Lam. If not, actually, you can even actually write it on the chat if needed be.
Yeah. So this is my contact details.
Yes.
Yeah.
Are you able to have one quick actually comment? If you are able to comment on the samples, how in complex systems, in very complex systems, how actually the samples that you're gonna use to drive actually the rules for the explanation, how it can be chosen actually to be able to cover all the behavior of the system that you are studying?
Yeah. So I think that this diagram. Yeah. So this diagram will be a good diagram to explain how
We are
to do
not,
the
we
samples.
cannot
Yeah.
see it. I think actually you are not, are you sharing?
Okay.
Yeah.
I'm going to.
Please, if there is any question in the pipeline, please go ahead. Also write it down or ask for the question so we can do it.
Mhm.
Yeah, please, Dr. Lam.
Yeah.
Yeah.
So I hope that everyone
Yes.
can see it now. Yep. So
Yeah.
this is the diagram. So when we talk about, for example, a two-dimensioned workspace, and then to x-axis, y-axis, and then to because one possible way to do the sampling, that is, we are going to separate this workspace equally, uniformly. Okay. So in each region, we are going to do some sampling. So that means we are going to come up with a local explanation for each region. But if we know that, what I mean uniformly, that is, if we do not have any information or knowledge about the data, and then we can just do something like that. But anyway, we come up with all these region. Each region will be a local explanation described by these rules all together. And we put all
Okay.
these regions together, it will become a higher level explanation using another set of the fuzzy rules.
Okay. Thank you, Dr. Lam. I think there is a question on the chat by Olivier Haas. So can you try to answer the question, Dr. Lam, if you can read it?
Uh,
How would that approach compare to other explainable methods applied to AI? Can fuzzy be the way between other AIs or
okay.
AI approaches?
So I think that I'm trying to understand what it means by other AIs. If we talk about, I don't know why every time the screen is not shared. Okay, yep. So I think that I'm going to share the screen again. So when we talk about other AI, I think that
saying it's just like deep
Uh,
learning or any
uh,
of the
please,
explainable AI.
Olivier, if you can actually, yes, please, you can ask the question directly.
Yeah.
Yeah.
So there's a lot of work on explainable AI, but they all focus on trying to make sense of data being sent in and out of massive networks. So I was wondering, in terms of approaches, does your approach, how does it approach compare to
Okay.
those that
So
use maybe physics or other things to explain the AI outputs?
I see. So for example, if you're going to use the physics informed controller or something like that, right?
Yeah,
Okay. So I think that um right here, when we talk about the XCF, it is controller agnostic or control method agnostic. So that means this framework is able to apply to any black box controller. But if we are talking about the physics informed controller, that means it is dedicated to a particular control action or particular controller. We need to know more about the model. We need to know more about the control action before we come up with that kind of explanation. So I don't mean that the physics informed controller that has any disadvantage. But what I mean that is when we talk about the explainable control framework, it is able to provide a control agnostic approach, and then so that would be for me it would be easier to apply because we integrate the fuzzy logic as well as the data-driven approach in order to provide the explanation. Yeah.
yeah,
Right.
I agree.
Yeah.
Okay. Thank you very much, Dr. Lam, for the presentation. And I think actually, as well, actually, this presentation will be on the YouTube webpage actually that we have. So there is actually a small comment in here actually before saying small comment. Originally, fuzzy logic, fuzzy rules are meant to be part of explainable AI. Do not you think if you try to find explanation for fuzzy reasoning, fuzzy rules, we would end up actually with infinite loop?
Mm-hmm. Yep. So I think that we are going to elaborate about this comment because fuzzy logic itself, it is interpretable and also it is a transparent model. But in the presentation, we already have some ideas. That is a transparent model and interpretable model. They are not necessary to be explainable in the sense that, for example, I come up with a model, I come up with a fuzzy logic system with 10,000 rules, and then so people can get some sense about it, but it is not possible to understand what it means. So the fuzzy logic system itself, the 1,000 rules, something like an abstract of a book. But how do we turn the abstract into something easy to understand? That is what the XCF is trying to do. We use the fuzzy model of the FMAE to translate those complicated rules into something easy to understand, and then so which will need to have one, the mechanism, and then the second one, that is the algorithm to reduce and aggregate the rules and then generate the indicators. These indicators will open the fuzzy logic and then work with the large language model to generate the the explainable report.
Okay. Thank you, Dr. Lam, again. Thank you, the audience, actually, for coming to today talk. And you have available actually the talk on YouTube, as I said, the YouTube webpage actually of the ACE network. So please, actually, we welcome you again actually for the next talk. Try to be supportive for our AI and data talk series. Thank you. Thank you, Dr. Lam. Thank you. Bye
Yeah,
bye.
thank you very much.